Dear students, in the subject elements of mechanical engineering and the module 2, we are discussing about the turbines. So in the previous video we have seen about the Pelton wheel turbine and the Francis turbine. Now we are going to discuss about the Kaplan turbine. What is Kaplan turbine and how it is differ from the Francis and the Pelton wheel turbine. We are going to discuss here. So the Kaplan turbine is a axial flow turbine, reaction turbine, and a scientist called Victor Kaplan was an Australian professor. He developed this in the year 1930, right? So he combined the adjusted propeller blades and automatically adjusted wicket gates for the getting the efficiency over the water flow and the water level. So here this type of turbine, we call it as propeller turbine, okay, and it will be normally used in the marines, and this is at low head level and high flow rate possibilities there where it can be useful. It is capable of working in the low level pressure head, okay, around the 10 meter height it is there. It will be working. So 10 to 70 meter, this is the working range of the head at which it can the Kaplan turbine works. And this is since it's a reaction turbine, we are going to see how it is going to be worked. The working principle is when the water leaves the blade, okay, due to the reaction force, the blade is going to be rotated, and the lift force which is created and the opposite direction of this, it will be going to be rotating. This is the logic over here, and the lift force is only going to make the blades to rotate. So here we can see the sketch of the Kaplan turbine. So there tail race is there, and from the top of the cross-sectional view of this Kaplan turbine, we can see a scroll casing. We call it as a scroll casing, the casing which covers all the parts of the runner blades, gate blades, and the boss. So all the shaft is covered with the casing. Casing avoids the splashing of water, as well as it's a safeguard all the components which is there required for the turbine blades to rotate. So there it is also a spiral casing, as in the case of Francis turbine. The water enters into the spiral casing, and through the gate vanes it will come, and it enters radially, then fall down axially. Axially in the sense to the axis of the turbine shaft. Okay, shaft is consists of a boss which having blades at its periphery. So the blades are going to be rotated when the water flows through the gate blades, and when it enters into this and it hits on the runner blades, the blade is going to be rotated because of the reaction forces. Then water falls down and it goes to the tail race, right? This is the logic behind this, and let me see one by one what is casing, what are the parts, how it is functioning, all the things now we are going to see. A scroll casing is that's what a spiral type of casing which is having a cross section, decreasing cross section. The water enters into the scroll casing when from the water inlet, and it flows in a decreasing area. That's a spiral casing, and it flows inside. The guide vanes on the runner blades are there inside, present here. So the guide vanes, or through the guide vanes, the water enters into the runner blade. So the guide vanes guide the water to flow in a proper flow rate. So the guide vanes mechanism, we can adjust the guide vanes with the help of some the instruments, and we can go. There is a angle tilting mechanism, so that we can guide the vanes, adjusting words which the vanes can guide the water, and it will hit on the runner blade. Okay, so these guide vanes will help to reduce the swirling effect of the water, because water is coming and it flows in the spiral area, the decreasing cross section area. When water comes, the swirling effect will be more. To avoid that, the guide vanes will be there present. It will directly safeguard the runner blades from this effect, and then it controls the flow of water, how much is required for producing the electricity. So if there is more amount of power requirement is there, then we can adjust to the guide vents in a way that more water can hit on the blades, or else we can control the flow of water by using the adjusting the guide vents. So the opening and closing depends upon the demand of power which is required. So in case of more power, if you want, then you have to open wider the gates, and if you want to, there is a less amount of power generation required, then you have to close the or close these gate vents, so that the water flow can be reduces. So in this case, the runner and the runner blade, after the water crosses the gate vents, that is the gate vent gate to the runner blade. The runner blade, it is located in a large boss in a shaft which is having a boss at this front, and in the large boss, the periphery, the circumference which have the blades are attached in the shaft, and that shaft is going to be connected with the generator. Okay, for production of power, we have to connect it to the generator. So the boss is attached with this, the blades are attached with the boss, and the boss is having the shaft which is connected to the generator. Now the water enters after the guide vents, and it will hit on the runner blades, so that the water when it leaves the runner blade, it will create a reaction force and it will start to rotate. So when the water leaves, it will it reduces the pressure already, it loses the pressure, and but the draft tube is here which will help to increase the pressure after when it is exist from the runner blades, because the water back pressure can create a cavitation inside the turbine blades. To avoid that, to prevent the backflow of water from the tail race to the turbine, we need a pressure development inside the after when releases from the turbine, so that the draft tubes will convert the kinetic energy of water which is coming out of it, and it makes through increasing the pressure of water which is coming out. So this draft tube, we can see the entire working now. The water, first it will start from the penstock, so water comes through the penstock and entering into the scroll case. When the water enters into the scroll case of the cross section, reducing cross section, it moves along the cross section, and it will hit on the guide vanes. The guide vanes guided to flow the water to the penstock, to the runner blades, and the runner blades, when the water leaves the runner blades, it produces the reaction force on the blades, and the boss is going to be rotated. The water leaves the blades, and through the tail race through the draft tube it goes. Okay, when water enter into the draft tube, the pressure is less, and when exits, the pressure is almost it is increased because of the gradual increase of the cross section of the draft tube. So this is how the Pelton wheel is going to be working out. This is the drawing, and the advantages is this is very smaller in size and very effective in low pressure head turbine areas where the pressure head is very less, and cavitation is a major disadvantages here. To avoid this, draft tubes and other things are used. Okay, use of draft tube, mainly it is used to produce the increase the pressure and to reduce the cavitation. So construction is easy, but the efficiency is very high as compared to other hydraulic turbine, and it is a low level turbine. That's what low we can say. Normally turbines is classified into high pressure turbine, medium pressure, and low pressure. Here it will act for the low pressure turbine and low head turbine, we can call it as. And that's what in the next video we will see about the pumps, what are the types of pumps over there, and these turbines will be applicated for the low head and high flow rates. Okay, thank you.